In this problem, we are given the following op amp right here. We are also told that it is ideal. We are then given our V of G right here as well, and we need to calculate the average power dissipated by the 1 kilo ohm resistor. We can see that our 1 kilo ohm resistor is right here, so it's going to be associated with our V0 value, and this is the voltage that is going to come out of our op amp. In fact, we're going to be finding the P average by using the voltage and the resistance. We are given the resistance, we are shown that right here, but we don't know our Vm, and this is the Vmax. The Vmax is the voltage that's coming out of here, so that's our V0. So we need to find that. And to find that, we're going to use the node voltage method. We are going to look at this node right here. This is our V of n for negative, and this terminal will be our Vp for positive. We know that our Vn and our Vp are equal to each other. And in this example, we can see that our Vp is connected to the ground here. We can say that it's grounded, and when it's grounded, we know it's equal to 0. So when we write our equation, just remember that our Vn is equal to Vp, which is equal to 0. Looking at our op amp, we have voltage here, so we are going to have to analyze the voltage over this way. We are also going to have to analyze the negative feedback that comes back over this way, and the negative feedback that comes back this way, and these both go into our Vn, so we're going to analyze them separately. Now we're going to write our actual equation. First, we have our Vn minus our V of G, and this is all happening over the resistance between them, which are these two resistors right here. This is the 500 nanofarads plus the 2 kilo ohm resistor. And after this, we are going to have a plus V of n, and we have this V0 right here, and it's going back because of the negative feedback, and it's happening over the 20 kilo ohm resistor. So we're going to have a Vn minus our V0 over 20 kilo ohms of resistance. And we're going to have the same thing, but over our 100 nanofarad impedance, which is a capacitor. And we're going to have the V0, or the Vn, sorry, minus our V0, and this is happening over our 100 nanofarads. And that's all set equal to 0. Now, to really do this, we need to convert some things. We need to find the XC equation for this. That way we have a J in here, and we can write it in the rectangular or polar form. And the same thing for here. That way we can analyze them as impedances and not just as capacitors. We need them to be in ohms instead of nanofarad. And we also know that our n, our V of n, is equal to 0. So when we rewrite our equation, we're not going to have a V of n anymore. To find our x of c, we can look in chapter 9, V-I relationship for a capacitor. And in this section of notes that's linked in the description below the like button, we can see that our x of c is equal to a negative j, and this is happening over our omega times c. And we know our omega is this 1000 right here. So when we plug this into a calculator, we're going to have a negative 1 divided by 1000 times our capacitance, which we are going to be analyzing the 500 nanofarads first. So it's 500 times 10 to the negative 9, because 1 nano is 10 to the negative 9, and this is going to give us negative 2000. We can write this as negative 2 kilo ohms, because the units is now going to be in ohms. That's what it would be when we do this conversion. And it's kilo because we have negative 2000. We know K is equal to 1000, and that's why it's in kilo ohms. Now we're going to look at the 100 nanofarad. It's going to be the same thing, negative 1 divided by 1000 times 100 times 10 to the negative 9th. And this is going to give us negative 10,000. We can also write this as negative 10 kilo ohms of resistance. Now, before we write this, I'm going to simplify a few things. I am going to cancel out the kilo ohms for all of these. And don't forget, because I almost just did, about this negative j. When we write our equations right here, it's going to have a j inside of it. We have the negative, but we didn't put the j in. So we have this now, and we can rewrite this so it's a little bit cleaner, and then clean it up once again after that. When writing this out, I just realized that we were given our V of G, and I totally forgot to plug it in. Our V of G is this equation right here, and we can see that at the beginning part right here, we don't have a Vmax, or it looks like we don't, but it's actually a 1. So we're going to have a 1 here. What we don't have is our angle. So we're going to set our angle equal to 0. This is the polar equation. If we were to write it in the rectangular form, to convert it, all we would need to do is have our number out front, and then we're going to, in parentheses, have the cosine of our angle, plus j times the sine of our angle. And if we do this, we're going to see that we would just get 1 and plus 0j as well. So this is also just 1 for the rectangular form. And I'm going to plug this into our v of g right here. Now I'm going to move this constant over to the right hand side, and then I'm going to combine our v naughts together. And this is what we're going to get from here. With this, I am going to divide this. In doing this, we're going to get a negative 0.05 minus j. It's minus because when we flip the j to the top, it becomes a negative 0.1. And this is in parentheses, set equal to our 1 over negative j 2 plus 2. Now we are going to divide both sides by this part. That way we can get v naught by itself. Now we are going to have to multiply these together, and multiply these together, and these together. And this is all going to be over 1. We're going to set v naught equal to, and then instead of just having 1 here, it's going to be 1 with our angle of 0 degrees. We're going to take this polar form because when we divide it, we need it to be in polar. And if we add these together, we're going to get negative 0.3 minus j of 0.1. Now to divide this, we are going to need to convert this into the polar equation. And to convert this, we know that we need a Vm, and our Vm is equal to the square root of our real number squared plus the imaginary number squared, and our theta is equal to tangent of negative 1 of our imaginary number over our real number. From this, we're going to get that our V naught is equal to, and then we're going to have the 1 over the angle of 0 degrees up top, and then approximately 0.316 on the bottom with an angle of approximately 18.4 degrees. Now when we divide this, we have 1 divided by our 0.316, and this is going to give us a V naught is equal to approximately 3.16, and then with our angle we are just going to subtract. Again, we divide these first two, the real numbers, and then with the degrees we subtract the bottom from the top. So we are going to have a negative 18.7 degrees. So this is going to be our V naught. And we know in doing this, all we actually needed was our V of m right here. And we know our V of m to be this 3.6. So we are going to plug our Vm into this equation. We're going to have 3.16, and this is divided by the square root of 2. Well, if we plug it into this greater equation, we have that our P average is equal to our RMS squared, and we know this is equal to our V RMS. So we are going to have the entire 3.16 divided by square root of 2 squared, and this is over the resistance. And we want to find the resistance of the power dissipated at the 1 kilo ohm resistor. So our resistance is 1 kilo ohms, or 10 cubed ohms, because we don't want to work in kilo, we want to work in the actual ohms itself. And now we can plug this into a calculator. And this is going to give us approximately 0.005. And the answer wants it in milliwatts, and this currently is just in watts. So we are going to multiply this by 1 milli, and we know this is equivalent to 10 to the negative cubed. So if we flip this over, it's going to be 10 cubed, and we can move our decimal 3 to the right, and we are going to get that we have a 5 milliwatt power. And that is going to be the answer for this problem. If you want more introduction to circuit analysis, there's a playlist and notes that go over the entire coursework for this subject in the description below the like button.